let me introduce our first speaker in the afternoon session, Barrau, who will speak about quasi-normal mode and the application to investigate fundamental physics, including quantum gravity. So Aurélien, it's great to have you here. The teams are yours.
Okay, thank you very much. So I am using this for the first time. So can you see my slides? That's okay?
Not yet.
Okay, let's hope.
Please use the share option.
Okay, let me try again. I think okay, let me try again. Share, okay. So you don't see my desk, right?
Not yet.
So what's happening? I tried with our colleagues yesterday and it worked. So let me try again. Okay, share. Okay, maybe it will be better now. So is it better?
It works.
It works. Right. Okay, sorry for the delay. Okay, so maybe it's even better like that. I hope so. Okay, so let me tell you a few words about quasi-normal modes of black holes and the way they can be used to investigate either modified gravity or quantum gravity. So we now observe colliding black holes. That's very good news. And we know that there are basically three phases. First, the in spiral, then the transient event in itself, and then the decay of the formed black holes through quasi-normal modes. So the fact is that black holes are very simple objects, actually, because they are just spheres of geometry. We are not concerned with equation of states or complicated matter or things like that. They are basically empty solutions of the Einstein field equations. And that's very fortunate because it means that when we study the way they relax, we have no dependence upon the kind of perturbation. We can really study the system in itself, and their decay is not, strictly speaking, made of normal modes, but of quasi-normal modes, just because the system is losing energy. It is an open system. We emit gravitational waves. So slightly more technically speaking, the quasi-normal modes are the poles of the green function. Okay, so okay. Oh, it seems that there is a little bug again. Sorry for that. Cool. Okay, so basically to investigate quasi-normal modes, you just have to linearize the Einstein equations, to linearize the metric by writing a small perturbations with respect to a background metric, and then to solve the resulting system. So basically, this is delta Ricci equal 0. So the boundary conditions are somehow unusual because you ask the waves to be purely outgoing at infinity because there is no source, and to be purely ingoing at the event horizon because, of course, by definition, nothing can escape the black hole. So writing down the radial part of the wave right here, you can basically decompose the complex frequency into a real part and an imaginary part. So the real part is the real frequency, and the imaginary part is related with the damping time. It's just the inverse damping time of the phenomenon. So when omega I is negative, we basically face an exponential damping. So this is a stable system. And if it is positive, we have an exponential growth. So it is said to be unstable. Of course, this is to be taken with care because when there is this exponential growth, the linearized equations are no more valid, and we don't exactly know what is going on. You know that mathematically speaking, only the stability of Minkowski space has been demonstrated, which is not a very exciting result for physicists. So those things are still being debated when going into the details of the rigorous treatment. Okay, so I don't know why this refuses to change. Okay, I'm sorry. Okay, so it's interesting to have a look at the equation of motion of field which is scattered by the black hole. It is not the same equation. It is something different from quasi-normal modes, but the fact is that the equations are basically the same. So what is written here is just the Klein-Gordon equation in the background space-time of the black hole with different values of S, depending you are considering scalar, electromagnetic, or gravitational perturbations. And at the end of the day, after a few change of variables, you end up with a kind of wave equation with a potential, which is very well known and which is given there. In the case of quasi-normal modes, things are slightly different because you don't try to solve the equation. You basically try to understand for which values of the frequency there are solutions to the equation. So when writing down the metric in an axisymmetric form, and you are allowed to do that because due to the spherical symmetry, you can always, with a rotation, go to an axisymmetric solution. And then you can immediately see that there are two kinds of perturbations. There are perturbations that give small values to the metric coefficients that were initially zero in the Schwarzschild solution. So this is omega, Q2, and Q3. And those perturbations inevitably induce a frame dragging effect, and they are called the axial perturbations. The other ones, that is, the perturbations giving small increments to the already non-zero metric coefficients, are called the polar perturbations. And on the lower right panel of the slide, I have written the axial and polar potential. And the very interesting point is that they are not at all the same. They share the same behavior at infinity and at the horizon, but they are obviously not the same functions, but still they lead to the same quasi-normal modes. So this property is known as isospectrality, and it is something quite profound that I will come back to later. So the quasi-normal modes of the Schwarzschild black holes are very well known. They are represented here. And depending on how you are minded, you can think either to a uterus or to a bull skull, but this leads to very nice features, depending on the overtone number which is considered and to the multipolar order of the quasi-normal modes that you consider. So last year, a nice paper was published in PRL showing that even in the first events detected by the LIGO collaboration, when really going into the details of the ring down phase, it can be shown that several quasi-normal modes have already been detected, not only the fundamental, but also at least one overtone and probably two overtones. So that's very good news because it means that physics of quasi-normal modes is now becoming part of experimental physics. So at this meeting, we all, of course, discuss beyond the JR, but just because we are physicists, it's good to take just a few seconds to keep in mind that going beyond the JR is really not something obvious. It's not because we all do that it is meaningful to do that, because, of course, the very well-known Lovelock theorem shows that basically JR is the only solution satisfying some quite general requirements. So if we want to go beyond JR, what I'm going to do in the next slides, we have either to allow for extra dimensions, to allow for violations of the weak equivalence principle, to add extra fields, or to allow for violations of diffeomorphism invariance. So I just mean that we have to keep in mind that this is not something which comes from free. For free, we already have to make strong assumptions to go beyond JR, and of course we need good motivations to try to do so. So I have written a metric. Okay, can you hear me?
Yes.
Is it working? Because I hear that my microphone has been deactivated.
Yeah, it works.
It's okay. It's okay.
So I don't know what has been lost. It has been deactivated automatically. I don't know why. So sorry. So here I've written a generic metric with a function f, which is not necessarily Schwarzschild, and we can compute the associated potential. And thanks to this potential, which depends analytically on f, we can evaluate the quasi-normal modes. You can play the very same game for an even more general metric with different functions a and b in front of the temporal and radial parts, and even in front of the angular part. Then the calculations are a bit more involved. You also define a kind of tortoise coordinate, but it's not exactly the usual one. You end up with a wave equation. You define this new parameter, and at the end of the day, you can still compute a parameter, a potential, which depends on the function h, on the function a, and the function b still appears through the definition of the tortoise coordinate. And thanks to this potential, you can again try to evaluate the quasi-normal modes. So in the following, I'm going to rely on a WKB approximation scheme, which is known to work very well for quasi-normal modes. This has been checked either with analytical values when they are available and with numerical simulations when they can be performed. There are basically 3 regions and 2 turning points, and the situation is rather under control, at least when considering n values that are smaller than L, that is overtones values that are smaller than multipolar values. So what I'm going to show you now are not results that are that have been calculated to be used for accurate predictions. I'm going to give high values to parameters that are expected to be small, so don't be afraid about that. My point is just to try to understand if we can see in quasi-normal modes some generic trains appearing in different theories of quantum or modified gravity, whatever the numerical values of the parameters that are involved. So let me first focus on massive gravity. So one of the first motivations for modern massive gravity was to try to account for the accelerated expansion of the universe by generating a kind of Yukawa-like potential for gravitation. The first tries were suffering from Boole-Desir instability, and this was corrected in the so-called DRJT version. And this theory also exhibits some interesting holographic properties. So basically, the action is the one written here, where U is potential, and this leads to a metric defined by the function given below, where lambda, the cosmological constant, gamma, and epsilon are not completely free. Those parameters are related, of course, with the mass of the gravitons. So on the plot that you can see on the lower right panel of the slide, I have represented different quasi-normal modes. So each theory of curve corresponds to different values of L, so L equal 2, L equal 3, L equal 4, and then each point when going from the back to the upper side corresponds to different overtone numbers, so fundamental, first overtone, second overtone, etc. The black dots corresponds to GR, and when you move from GR to the right, this is an increasing of the deformation parameter, and in this case of the graviton mass. So in this specific case, what you see is that the imaginary part of the quasi-normal modes is increasing. So it means that the frequency is increasing, and the real part, and the imaginary part is also slightly increasing, which means that the damping is increasing. So we have both effects at the same time with a relative amplitude, which is of the order of 50% for the imaginary part when compared to what happened for the real part. For modified SVT gravity, so we allow the gravitational constant, a vector field coupling, and the vector field mass to vary with space and time. The idea was basically to try to explain the rotation curves of galaxies without dark matter. We know that this theory is now under pressure for several reasons that we have probably all heard about, but still it is still being considered. and studied, and we have tried to figure out what it leads to for quasi-normal modes. So we focus on a specific case where a B mu nu, which is given here, has a nonlinear structure because the phenomenology is richer, and we require the renormalization of the Newton constant to be such that we have horizons. Otherwise, we don't have black holes, and of course, it's not very interesting. So the metric function is basically the following one, and it's controlled by this alpha parameter. And what you see is that in this case, the real part of the complex frequency is still increasing when you increase the deformation, but the imaginary part is not changing at all. So it means that the damping is not affected by alpha, but of course the frequency itself is affected. In Orjava-Lifshitz gravity, one basically bets on the fundamental nature of the quantum theory instead of relying on general relativity principles, which means that a renormalizable UV-complete theory of gravity is built, but it is not a priori Lorentz invariant in 3+1 dimension, and the usual covariant time only emerges at large distances. So the structure of the theory is a bit complicated, but it can be summarized in this function f, which is given here. And the quasi-normal modes are once again depicted as a function of the deformation parameter. So once again, the frequency is increasing with the deformation, but this is the only case where the imaginary part, the opposite, the absolute value of the imaginary part, is strongly decreasing, which is an interesting feature. One can also focus on so-called generic H-bar corrections. So here, you know, you don't pick up a specific quantum theory of gravitation, but you just calculate loop corrections to the Newtonian gravitational potential. So this is somehow a quite universal result, although there have been a lot of controversies about the sign of gamma, which is sometimes assumed to be positive and sometimes negative, but right now there is a kind of consensus that it should be negative. And you end up with this kind of behavior where the frequency is decreasing, sorry. This is the only case where the frequency is decreasing with the deformation parameter, and the damping time is basically unchanged. Then you can go to loop quantum gravity. So loop quantum gravity is a tentative background invariant and non-perturbative quantization of JR. In this framework, a black hole is usually described by the intersection of an isolated horizon with a spin network, and you end up by calculating quanta of area that are associated with the punctures of the network, each puncture carrying out a quantum number which is associated with the representation of SU2, which is selected. There are many proposals for black holes in loop quantum gravity, so it's hard to pick up the solution for black hole in quantum gravity. So I have here selected one approach, which is called the polymeric black holes. And basically, the idea is to solve the Hamiltonian constraint by replacing the connection by its holonomy, as it is usually done also in loop quantum cosmology. So the effective resulting metric is given there. The A0 constant is related with the minimum area gap of loop quantum gravity, and the R star, which appears here, is related with the polymerization parameter. And when varying the parameter, we have this interesting behavior which is non-monotonic. So you start with JR, then it goes to the right, and it comes back to the left, just because at some point there is a compensation between the effect of the existence of a minimum area gap and the effect of polymerization in itself. So to conclude on this, I would say that distinguishing between the models I have just sketched with quasi-normal modes is very challenging. First, because there exist many degeneracies for given overtone and multiple numbers between the models, when taking into account, of course, that the values of the parameter controlling the deformation are by definition unknown. Then the intrinsic characteristic of the observed black holes are, of course, also unknown in real astrophysical situations, and this add up other degeneracies. And of course, real-life black holes are not Schwarzschild black holes, they are Kerr black holes, and this would also add up degeneracies. So it's very complicated to use those measurements to really determine the parameters, but some interesting and generic trends can be underlined. For all models, the effect of modifying the gravitational theory are more important for the real part than for the imaginary part of the complex frequency. And some trends are specific to each model. We have not found any two models with the same kind of behavior. And in addition, the sign of the frequency shift and its dependence upon the overtone and multiple numbers is characteristic of a given extension of GR. I mean, of course, it's not a theorem, but when considering the models that are much discussed now, it seems to be true. So if features beyond JR were to be observed in the future, the direction of the frequency shift in the complex plane would probably allow to exclude several models. This is what we have shown. And I would like also to point out this old idea that has been discussed much in the past, which is to try to relate the quasi-normal modes, at least in some asymptotic limit, with possible quantum gravity effect, just because the integer which appears here might be related with the minimum area gap that could appear in the spectra of black holes. Once again, this is not a simple idea. Some problems have been pointed out, but this is very interesting to try to revive this idea in the context of modern quantum gravity. So let me now focus on a model of quantum gravity, which is rather naive, but quite appealing just because it is simple, and I think it makes some sense, not relying on a specific theory of quantum gravity. So the model was pointed out by Rovelli and Agar, and the idea is basically the following. We know that the curvature scale is basically given by R to the minus 0.5, where R is a Quatermain invariant, just defined by this contraction over the Riemann tensor. But the problem is that if we just evaluate the quantumness of space-time by taking the ratio of the Planck scale over this curvature scale, we disregard cumulative effects. And we know that cumulative effects could be important, the paradigmatic example being the decay of a radioactive nucleus. If you wait 10 minutes, nothing happens, but if you wait 1 billion years, of course, the nucleus has disappeared. So the effect is huge. So the hypothesis of Rovelli was to measure the quantumness of space-time with this parameter, which is basically the product of the Planck scale, the Quatermain invariant, and the proper time. So there are arguments given in the paper.
Sorry, Aurélien,
yeah.
There's a question by Chun-san.
Oh, yes, may I ask a question? Is this term ghost-free? This R to power minus half R is defining this square of Riemann tensor. Is this term ghost-free?
Sorry, can you say it again? Is this term what?
Ghost-free, free from ghost instability.
I'm not sure this is really relevant because what do you mean? Because the problem of ghost appears when you try to build a dynamical theory, right? Here we don't build a dynamical theory. We just want to have a kind of evaluation of the curvature scale on a given manifold. So I'm not sure this is really relevant, right?
Okay, thank you. Please go ahead.
We can discuss later, sure.
Oh, yeah, sure.
The proper time is trivially related to the Schwarzschild time, and therefore this quantumness can be explicitly calculated. And the reason why it is interesting, or at least appealing, is that when you evaluate the maximum of this function, it is outside the horizon. You see that the maximum is reached at R equals Schwarzschild radius times something which is greater than 1. So this is why this line of thought is interesting, because it means that when taking into account the time integration of possible quantum gravity effect, something might show up outside the horizon. Well, it is not grounded in a very serious model. It is not grounded in a fundamental theory of quantum gravity. This is basically dimensional analysis, so I would not bet my life on that. But at least this is an interesting result for phenomenology. So we have tried to modelize a possible deviation with respect to the Schwarzschild metric by a Gaussian function, because we wanted something that can be adapted to different models, so which is completely defined by its amplitude, position, and width, and to calculate, once again, the quasi-normal modes. So here are the results. So once again, for different values of L, and for each series of points, when going from the back to the upper side, you increase N. Black is general relativity, and blue is this toy model for cumulative quantum gravity. So on the next slide, we have plotted the relative variation of the real and imaginary part of the complex frequency with respect to the position of the Gaussian deformation and width of the Gaussian deformation, and for a fixed amplitude of the deformation. So the results are not very surprising in the sense that when the deformation is very wide, you are not sensitive anymore to its position. This is somehow trivial. But when the deformation is peaked, then you see that the maximum effect for the quasi-normal modes appears for mu equal 3m, which does not come once again as a surprise, because 3m is the photon sphere. This is the maximum of the potential. So this is where the possible quantumness could be easily investigated. For the imaginary part of the complex frequency, the effects are more complicated, and there is a change of sign when mu is changing its value. And the last plot just shows the effect of changing the sign of A, that is the sign of the deformation itself. So here I have plotted the numerical results that can be used for anyone playing with a toy model. So what is plotted here is basically the coefficient x, because the relative variation of the frequency, either real or imaginary part, is linearly varying upon this deformation A, and x is the amplitude of the deformation. And this slope, to some extent, is plotted here as a function of L for different values of mu and for a fixed sigma. So what this basically means is that you can use those results for your preferred model of toy quantum gravity and just investigate how much and in which directions the quasi-normal modes will be displaced. So now we can put order of magnitudes and go back to the idea of Rovelli and say, okay, so let's assume that we are lucky and this toy model is meaningful. Can we see something with real-life black hole? And the answer is yes and no, because when you put numbers, you end up with the result that you see something if the mass of the black hole is of the order of the moon. So if you are an astrophysicist, this is a ridiculously small mass, because we know that, of course, astrophysical black holes are heavier than the moon, so it just doesn't work. But if you are a theoretical physicist, of course, this is way bigger than the Planck size, than the Planck mass, and this is very good news, because it might mean that we have quantum gravity very far away from the Planck scale. So depending on your viewpoint, this is good news or bad news. But still, there is this idea that if we play with quantum gravity, there might be a pre-Big Bang phase. And if there is a pre-Big Bang phase, and if black holes, as it seems to be the case, survive the Big Bounce, then they can be much older. And then you could see this effect even for higher masses black holes. But of course, this becomes quite exotic. We have also applied the same line of thought to the Hayward metric, which is quite interesting because it is once again a toy model for quantum gravity, which takes into account rigorously the possible time dilatation between the center of the black hole and infinity, and which reproduces a one-loop correction, at least in some approaches. And we end up with the result that the quasi-normal modes displacement could be measured by the next generation of experiment. What I have in mind is the Einstein telescope that was described this morning for an L over m of the order of 0.7, which is obviously not promising at all for astrophysical black holes, unless some scale much larger than the Planck scale enters the problem. Okay, so now let me go slightly away from quasi-normal modes and focus on the so-called gravity factors. So gravity factors are closely related with quasi-normal modes, but they are not exactly the same thing. So this is basically the Hawking radiation spectrum of an evaporating black hole with a temperature T, which is basically 1/m. And we all know that the Hawking spectrum is nearly thermal, but not exactly thermal. And the non-thermal part is encoded in this cross-section here, which is basically obtained by summing over the amplitudes, those amplitudes being evaluated by computing the scattering of a quantum field in the background of a black hole. So I used again the polymeric black hole scheme that I presented before in loop quantum gravity. So in this model, we have a kind of mini superspace solution inside the horizon, which is analytically extended away from the horizon. In my opinion, this is not a definitive answer. There are weaknesses in this approach that are known, but it is an interesting first step, I would say. So in this situation, you can compute explicitly the scattering equation and the associated potential, which is given here. So it's a bit involved because, you know, we don't have the same function here in front of the dt and in front of the inverse dr. So this is why the calculations are not straightforward. And you end up with this kind of plot. So the upper plot is the cross-section as a function of the frequency of the field normalized to the inverse mass of the black hole in JR. And when you go from the top curve to the low curve, you increase the polymeric deformation parameter. So the effects are not huge, but basically what you do is that you slightly decrease the cross-section and you slightly shift the different maxima. And intuitively speaking, if you are not used with this physics, the different bumps correspond to the resonant interaction of the quantum field with the black hole. You have two scales in the problem, and therefore you expect this kind of patterns. This was for scalars. You can do the same for fermions. So this becomes very unfriendly because you have to go through the Newman-Penrose formalism and to solve the Dirac equation, which is not very user-friendly, but it works, and you end up with something which basically has the same kind of structure and behavior. And you also can investigate the effect not only of the polymerization parameter, but also on the minimum area gap. So the result is that generically what happens is a slight decrease in the cross-section, which in principle could be observable. This is something that is related with something that can be measured, but in practice, we have never seen an evaporating black hole. We are quite far from investigating tiny effect on the evaporation itself. But it could also be used to refine a study like the one we performed with Cao, Nui, and Perez a few years ago, when we investigated some effects due to the discreteness of the area in loop quantum gravity, but we neglected the associated gravity factors. So now they are computed and they could be used to have more accurate results. As I am now discussing the evaporation of black holes in quantum gravity, I would like to underline also another perspective that could be revived for several reasons right now, which is the idea to take a kind of local view. Because, you know, there was long ago this Bekenstein-Mukhanov idea that the area of a black hole is basically the n times the Planck area. It makes sense, but it is not the case in loop quantum gravity. In loop quantum gravity, the area spectrum becomes dense for high values of the area, and therefore the idea that it was not possible to see any quantum gravity effects unless we are very, very, very close to the Planck scale. And it might be wrong because instead of considering the full spin network associated with a black hole, it might make sense to consider the Hawking evaporation just from the change of state of a single quantum and not from a reorganization of the full spin network. And if you think in this way, first to recover the Hawking characteristic in the classical limit, so hopefully, and then the very interesting point is that you can have in principle detectable effects for any mass. Of course, you need the mass to be not huge, otherwise you don't have evaporation at all. But you can still consider a mass, I don't know, of 10 to the 10 grams, which is way bigger than the Planck mass, and the discreteness of the spectrum will still be there. And the interesting point is that I have calculated also the background of gamma rays coming, you know, from the decay of neutral pions, because if we have a line structure, it will be very easy to see from the emission, the direct emission of gamma rays from the black hole. But the problem is that the black hole also emit quarks, and the quarks form hadrons, and the hadrons do decay, and the decay of hadrons produce a continuum background of gamma rays. But the good news is that even when you take that into account, you can discriminate the line from the background, and the dynamics also does not wash out the effect when you time integrate. Because of course, at a given time, the spectrum is very well defined. But when you integrate over time, the lines are also displacing themselves. But hopefully, this does not wash out the effect. And the important point is that specific low quantum gravity features could also be measured and allow to distinguish between a kind of Mukhanov vision and the accurate spectrum of low quantum gravity. Okay, let me go back to quasi-normal modes and to this fundamental property of isospectrality. So as I told you, isospectrality is the fact that axial and polar perturbations do share the same spectrum of eigenfrequencies, although they are not described by the same potential. So this is not something obvious. So with Flora Moulin, we just went through again the full calculation, the historical calculation by Chandrasekhar, which is not very cool, and try to understand how it can be generalized with a metric of this form. And the result we have obtained is that the way of treating the problem by Chandrasekhar can only be generalized to this kind of function B. So this is interesting because this kind of function B, forget about the details, I'm sorry for writing them. This function B is exactly a Schwarzschild de Sitter or Schwarzschild anti-de Sitter black hole, right? Because this is a cosmological constant. So that's quite funny because here you don't really use the Einstein equations, but still you end up with a solution which is very well known in general relativity. I don't mean that isospectrality fails for other black holes. I just say that the proof of Chandrasekhar cannot be used in other cases. But this is not a theorem proving that isospectrality fails. Okay, this is something different. But at least this is clearly demonstrated for Schwarzschild de Sitter and anti-de Sitter black holes. It was known numerically, but it was still debated at the analytical level. So to finish, I have 10 minutes, something like that, right? So to finish, let me now focus on other, maybe more exotic approaches to black holes in quantum gravity. So there was this idea by Rovelli, Vidotto, Agar, and a few others a few years back, a couple of years in the past, maybe slightly more, of bouncing black holes. So black holes evolving into white holes due to non-perturbative quantum effects with a characteristic time of the order of m squared. So m squared is very interesting because it is smaller than m cubed, as long as m is greater than the Planck scale, and m cubed is the Hawking time. So it means that in this model, the black hole would bounce before it evaporates. So this is a trivial Penrose diagram. So this is Minkowski, this is Schwarzschild due to Birkhoff theorem, and this is the quantum region. So we have tried to investigate the phenomenology of this model. And the question is, what is the energy emitted by the bouncing white hole? And there are two different possible answers. One answer was the one pointed out by Rovelli, saying that, well, there is basically just one length scale in the problem. So the typical wavelength of the emitted signal is the size of the black or white hole, just because this is the only scale of the problem. It makes sense. This is what happens, for example, for the Hawking evaporation. But there is another way of thinking, which is to say, well, that's not that simple, because this black hole was formed in the early universe. the mass to be small. For an astrophysical black hole, the process is irrelevant. And so it is a primordial black hole for sure. And if it was formed in the early universe, which was radiation dominated, then we know what it was made of. We know what the null collapsing shell was made of, at which temperature. And just because the process is symmetric, what goes out is basically what went in. So there are two different hypotheses for what is released by the black hole. So we have shown that we can explain some fancy astrophysical effects, for example, the Fermi gamma ray excess. Well, let's be honest. It's much more probable that those astrophysical effects, for those of you who don't know, this is an excess of gamma rays coming from the center of the galaxy. As I was saying, I would bet my life that it comes from astrophysical effects, okay? But still, it's interesting to understand whether the same model could account for different astrophysical or cosmological effects. And what I like about this idea, it's not really to be able to explain that, because when playing with the parameters, this is not impressive, is that we have a very specific redshift dependence. This is what I like. In this model, when you look at sources that are far away, the way that the signal depends on the redshift, which is the one in yellow, is not at all the same that for any other source. Whether you take whatever you want, neutron stars, decaying dark matter, whatever you want, it will be the blue curve. In our case, it will be the yellow curve. Just because when you look far away, it means that the black hole has bounced long in the past, and therefore its mass was smaller, and therefore it was formed earlier in the universe, and therefore the temperature was higher, and therefore this compensates for the redshift. So you can do the calculation, but this is the idea. So we have shown that they can be seen quite far away, because any event basically up to the Hubble radius can be measured with some fancy features here that are either due to experimental effect or to physical effects. The dependence of the expected signal over the mass spectrum of the primordial black hole is weak, and this is good news because, of course, there are many unknowns in this physics, and if you were highly depending on the details of the formation mechanism, for example, it would spoil the hope to detect that. And more importantly, we have very recently shown that if we take into account the stochasticity of the event, because of course you cannot just say the lifetime is m squared, right? This is a random process. This is just like a nuclear decay. So this m squared is just a characteristic time scale, but this is a tunneling process. Then it works much better, and you can better explain the fast radio bursts that were exciting Ravelli at the beginning. Then those same people, with a few others, refine their model and say, well, probably we should not say that the bouncing time is m squared. We should let the black hole evaporate, and then the probability to bounce into a white hole is given by the usual instantant calculated by the Euclidean action. And basically the idea is that the black hole evaporates, it shrinks, and when it reaches the Planck scale, then it tunnels to a white hole. But the interesting point is that this white hole is long-lived, with a time of life of the order of m4, where m is the initial mass, right? Not the Planck mass, the initial mass of the black hole. So the idea came immediately that this could be a good candidate for dark matter. Unfortunately, we are just now with my student showing that it's very hard. It's very hard because it's not possible to explain dark matter like that with the formation at the reheating of after, because we will not be able to escape the strong constraints from nucleosynthesis. It is not possible to form those objects before inflation because their density would be non-realistic. And the only possible window is to focus on matter bounce scenario without inflation. But even in that case, we found some tensions with the background. So my own conclusion is that that's not a good candidate for dark matter. Okay, so I have finished. I just point here a special issue of the Universe magazine that was published under this title, Probing New Physics with Black Holes, and I invite you to, in particular, look at the nice papers by Giddings, trying to to see possible quantum effects in the images of black holes produced by the Einstein Event Telescope, which I think is a quite motivating possibility. Thank you.
Thank you, Aurélien. Thank you for a very interesting talk, a very inspiring one. So let's thank the speaker. You can express yourself at the chat site. Okay, are there any questions? We have a couple of minutes for questions. Sudo is raising hands.
Yes, I have a question. I have a quick. So Aurelia, you mentioned this polymerized black hole. Which model are you specifically focusing on? Is this the one by Nui and Gibril and others, or?
No, it's the one by Modesto. The one by Nui is very nice. I like it I like it a lot. It is using a kind of deformed algebra approach, which I have myself used in cosmology, so I'm fond of that. The problem is that it basically leads to nothing new outside the horizon. So maybe the model from Nui is better, in my opinion, at the fundamental level, but from the phenomenological viewpoint, the result is just that we recover JR. So that's all.
Right. The reason why I ask is, I mean, we also have an exact same model about this deformed black holes with Martin and Donghan. But the reason why I'm asking is because we worked on a different model of this polymerized black holes, which is due to Norbert and collaborators. And I think qualitatively, the result for the QNMs are the same. So we calculate the QNMs. The model was by Norbert and others.
Okay, thanks a lot. Anyway. I will look at this work.
Yeah, thank you.
So any other questions, comments? Yes, Michał.
So I have a question about this this simple idea of quantum gravity that you presented. This stuff that wasn't really based on any fundamental theory.
Yeah.
That you showed in certain points. Yeah, this guy. So here you present that in the context of astrophysics, and I wonder if you take this approach to cosmology, did you have any results? Like in particular, I'm thinking. If you would take eternal inflation, so like unbelievably long time of de Sitter expansion, and you would implement this idea, then you would have lots of time to pile up the effects of the quantum gravity. Would it anyhow work like this?
That's an interesting proposal. I don't know how we'll measure curvature in this case, and what would play the role of the proper time, but okay, I see the point. The problem is that in this approach, what they don't have any clear prediction. So for the case of black holes, that's quite easy because now we have very nice images, and they say at R equal this value, we expect something unusual, and we just have to look and to know whether this happens or not. In the case of cosmology, of course, it would be probably much more complicated, but okay, I will think about it.
No, the prediction would be, if, for instance, if there would be a big effect coming from a very, very long period of inflation, the prediction would be that there is an upper bound on number of e-folds, that inflation can't be too long, that the de Sitter phase can't be too long.
Yeah, okay, I see what you mean. But you know, there are already a lot of work about the de Sitter space because de Sitter space has already a non-vanishing temperature, etc. So there are also thermal effects. So okay, that's a good idea. But then I think I'm afraid we need to be a bit more quantitative in this framework. But I see the point. Thank you.
Okay.
We have another question by Francesca.
Oh,
yeah.
Okay, there.
Hi, I'm very curious about what you said in the end because I'm interested in the double bounce, the bouncing model with the matter bounce and bouncing black holes. So can you just say a word about what is the main problem? What is the tension with the background in a matter bounce scenario?
Okay, so once again, my critics are not at all on the model itself. I personally like the model very much, so I believe that the model makes sense. It's just a problem with using the model for dark matter, right? The problem is that whatever the way the bounce happens, something will be released by the white hole. So we made two extreme hypotheses. One hypothesis is that just the white hole decays by emitting one Planck quantum, because it has Planck mass, so it just emits one Planck quantum. And this is very easy to exclude. This is just not compatible with what we see in the universe. But the other possibility is that it just emits a very low energy background, because this is also possible. And I think you and Carlo, or I don't remember, you or Carlo, pointed out this to me, that the dispersion relations are not monotonic in condensed matter physics, and therefore you can have something very small emitting very low energies. So this is very exciting, and in this case, there is still a window which is opened, but yet that it requires some fine-tuning. So I will show you the plots very soon.
Okay, thank you.
Thank you, Francesca. Any other questions? Maybe just a very little one from my side concerning quasi-normal modes in loop quantum gravity. There was a paper, something like perhaps 20 years ago, by Olaf Dreyer, which attracted some attention, which was, I mean, concerning some observation that the area gap might lead to the quasi-normal mode. I think that was the first paper on quasi-normal mode in loop quantum, in the context of loop quantum gravity. Like, could you make a comment on that from the current perspective? I mean, is it relevant or not?
Yes, I think so. When you try to revive this idea and carry out a calculation, you basically fix the Barrau energy parameter. So that's quite exciting, and you end up with a value which is not exactly the one which is usually chosen to explain the entropy, but which is not very different. It is of the same order of magnitude, but it's not exactly the same. So I don't know exactly what to do with that, because it really requires, it relies on a very strong assumption, which is not a proof in any way. But yes, it would be interesting to consider it again.
Okay, thank you. So thank you, Aurélien, once again for the great talk.